This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today is strong acid versus weak acid, then strength of acid, strong base versus weak base, strength of base, ionization of water, ionization constant of water, and pH scale, and some related problems. So here we will see the comparison between strong acid versus weak acid, how to know which acid is strong acid and which acid is weak acid. So here in general, if we consider the formula of acid is HA, where H is it signifies hydrogen atom and A is basically the other part of the rest of the part of the acid. And as if after dissociation, it is giving the proton H plus, which is this white colored sphere, and the green color sphere, that is the rest of the part, that is A minus, the anionic part of the acid. So when these molecules are dissociated, in the left hand side, this is in undissociated condition. So when it is undissociated condition, that is denoted by this color as you are seeing here. But after dissociation, now all the HA molecules of acid that are present in the solution, all of them are in dissociated condition, maximum. So here you can see now this HA, which is denoted by this color, they are now in H plus state, which is the cation, and A minus, which is the anion. So H plus cation and A minus anions both are now present in the solution. So all the HA molecules, they are now in dissociated condition. And this type of situation will arise when we will take any strong acid. Okay. Now, if it is so, then what about weak acid? In case of weak acid, now the dissociation is not complete. So see, this is before dissociation and this is after. But the same thing, if you look in the right hand side, now it is different. Here HA denoted by this color, but after dissociation, the height is almost same. So they are here, this height is basically signifying how many, what is the percentage of HA that is now in dissociated condition, that you can understand from this height difference. So here the height is low, here the height is high, but this difference is very it is almost as if there is no difference, right? In the previous case, here you can see this color is not present in the right hand side because all of these molecules, they are in dissociated condition. But here most of these molecules, as you can see, most of these molecules, they are in undissociated condition. So that is the reason H plus, which is denoted by this white color, and A minus, which is denoted by this deep green color, that the height of these two parts, that is very low, but here the height is very high. So this is weak acid. So very less percentage of HA molecules, now they are in dissociated condition. So as a definition, we can say a strong acid is the one that is almost completely dissociated in water. But if it is weak acid, there will be partial dissociation. Okay, so that is the difference between strong acid and weak acid. Now, if we take this general formula for acid HA, when it is present in water medium H2O, in bracket it is mentioned liquid. Now this HA, which will be generated from HA, that will combine with H2O and it will produce hydronium ion, and the remaining part is A minus. You can also write this HA like this without considering H2O. If you write this, that is also fine, because H2O, it is present in very large amount compared to HA, because this is a solvent. So even if we avoid this, that is fine. That is HA is dissociated to H plus and A minus. But if you consider it, now you have to write H plus in the form of H3O plus, aqueous state, A minus aqueous. Now there is equilibrium between these two sides, right? So when there is equilibrium, the corresponding equilibrium constant, here we have written it as Ka. Now A, this subscript, it signifies basically acid. So acid dissociation constant or we can say ionization constant of the acid HA, that is whether it is strong or weak, that is not important. But if you consider this equilibrium for the dissociation of the general formula of acid HA, then the corresponding equilibrium constant Ka, that should be represented like this. So here we have, look at numerator and denominator. Numerator we have concentration of the species that are present in the right hand side, divided by, in the denominator we have the HA concentration which is in the left hand side, and we have omitted H2O because it is present in large excess. So if you omit it, its concentration doesn't change with time, so that is why it is omitted. Now Ka, you can also represent it like this if you are not considering water. So H plus concentration A minus divided by HA, undissociated HA, which is in the denominator. So if you write the ionization equation in this way, then Ka expression will be like this. So either this or this. But Ka, remember this is equilibrium constant, but equilibrium constant for what type of process? It is ionization or dissociation of the acid HA. Strength of acid. So strength of acid basically, that is whether it is high strength or low strength for the acid, that is whether it is strong acid or weak acid, that idea you can get if you know the value of this Ka. So as you can see in this table, there are different values of dissociation constant of the acid HA that is given here. The values of Ka in the right hand side column, and we have the name of the acid in the middle column, and the formula you can see, that is the acid formula, in the first column. So the value of Ka, just take this acid HNO3, which is basically nitric acid. So nitric acid, when you take it in water medium, in bracket it is mentioned aqueous. So all the values that you are seeing in this table, they are basically in water medium, which is clear from this expression AQ in the within bracket that is mentioned after the formula of the acid. Very large mention for these three acids. That means Ka value is very high. So it is so high. So this information, it means what? It means that these three acids, they are very strong acids. So when you take them in water medium, that is water as solvent, 100% dissociation will be there. So if there are, in simple words, if I say suppose there are total 10 molecules of HNO3, so all the HNO3 will be now dissociated in the form of H plus. You can also write H3O plus, both are basically same thing, and NO3 minus. So in this case, if you consider the formula HA, H is same as, that is H, but A part is basically NO3. Similarly for HClO3, HClO4, H and ClO4 minus, which is basically the anionic part A minus. Fine. Then as we are moving down, gradually the values are becoming less and less. And here this arrow, which is towards upward, it means increasing acid strength. So when you are moving from towards upper side, basically the values of Ka, it is increasing. And as it is increasing, which signifies that as we are moving down, the strength of acid is decreasing. That means gradually we are moving from strong acid towards weak acid. So very large for the first three. Then we have values with power of 10 minus 2. Now these values are for HSO4 minus, HClO2 minus. Now this is neutral, but HSO4 minus, though it is anionic, but and this anion basically generates from the acid H2SO4, right? But as it can donate H plus, so you can also consider it as if it is acid. It will behave as acid. It is basically bisulfate anion or hydrogen sulfate ion. Both are any name you can use. So HSO4 minus, here the value is 1.2 10 to the minus 2. But H2SO4, if you consider, where it is neutral molecule without any negative charge, that value is very high. That means H2SO4, it is very strong acid, but the anion HSO4 minus, this is not so strong, which is clear from this value. Then we have, as we are moving down, 10 to the power minus 4 for these two acids. Then it is minus 5, ethanoic acid. which is nothing but acetic acid, CH3COOH. Here it is written in a different way, but actually it is CH3COOH or acetic acid. 2 carbons are there, so the name we are calling it like ethanoic acid. So C2H4, C2H4, total 4 hydrogen and O. The formula is same. It is having power 10 to the minus 5. Then we are having minus 8, minus 10. So NH4 plus, this can also behave as acid because it can donate H plus, and the other part will be removed in the form of H plus plus neutral molecule. It is not necessary that the other part it will always be anion. That depends on your starting species, which you are considering as acid, whether this starting species is cationic or anion. So as it is already cation, it is already carrying some positive charge. So after dissociation, it will be H plus and neutral molecule NH3 ammonia. Similarly, starting species which you are considering as acid, if it is carrying some negative charge, and after dissociation it will produce H plus and sulfate 2 negative. So here we have 2 negative charge because already there is 1 negative charge and further we are removing H plus, so 2 negative charge over SO4. But the important point here in this table, as we are moving down, the values of Ka is decreasing, which is clear from this power of 10. This power is most important, not these values. And as we are moving down, it is becoming weak acids. So how to know which acid is strong or weak? Because when 2 acid values are given, you can simply compare and you can say that between these 2 acids, this one is more acidic, this one is more strong compared to the other one. But in general, how to say that which acid you should consider as strong and which you should consider as weak? Then you have to remember this fact that generally acids where Ka value is greater than 1, they are considered as strong. So in this case, they are basically greater than 1, they are strong. But as you can see here, 1.2 10 to the minus 2, which means what? It is actually 0.012. So 0.012, it is obviously less than 10, right? Actually, it is even lesser than 1. So when you have acid where Ka value is greater than 1, you can call them, you can consider them as strong. And if it is lesser than 1, as in this case 0.012, actually all these acids 0.012 and another one, they are also lesser than 1. Lesser than 1 means it will be fraction. It is no longer a whole number. They are considered as weak acid. And if you have any values in between 10 and 1, so it is in intermediate zone, right? As strong acids are essentially 100% ionized. So all the molecules will be in ionized form in the H and H plus A minus form. The concentration of the acid in the denominator is nearly 0. So remember the expression of Ka in the previous slide we have seen. The expression is H3O plus, then A minus, and in the denominator we have Ha, that is undissociated. So when it is strong acid, as it is 100% ionized, that means initially you have started with undissociated Ha. But if all the molecules are in dissociated form, obviously the concentration of Ha, that is actually 0. So the denominator is 0. The concentration of acid, that is basically Ha within third bracket, which denotes concentration of acid, and it is present in the denominator, it is almost equal to 0. So when it is 0, that means the value of K is very, very high. Almost it is approaching infinity. So that is the reason that K values are generally reported only for weak acid, because when you are having any strong acid, the value of K, it has no significance, which is it is so high. So in this case, see HClO3, HNO3, HCl. If you are considering, if you are comparing them for all these acids, the K value is almost approaching infinity. Okay, so they will be strong, and we are not interested in their Ka values because in all these cases there is 100% dissociation. Okay, so what is the significance of Ka value? Significance of Ka value will only be there when you have some weak acid where dissociation is that is so that K value is fraction. Then only the value of K matters. So for example, as you can see here, if you consider the, that is except the first three, if you consider the other three, if I am comparing acetic acid and hydrocyanic acid, so acetic acid 10 to the minus 5, hydrocyanic minus 10. So now you can compare these two and you can say that acetic acid comparatively stronger. It is not strong acid, but compared to ACN, it is hydrocyanic acid ACN, its strength is high. So now the value of Ka, it has some significance. So you will see that whenever we talk about ionization constant, that is Ka, or dissociation constant for any acid, it is mostly for weak acid. We do not talk about Ka values for strong acid. It is only for weak acids, right? So same type of discussion we can also have for base, right? So strong acid, weak acid, we now have idea. But what about strong base? Strong base, just like strong acids, they will also dissociate completely in water and they will produce hydroxide ions. Here we have some examples. Suppose if you consider the elements of group 1, elements of group 1 is lithium, sodium, potassium, then rubium. If you, lithium, sodium, potassium, rubidium, then cesium. If you consider these group 1 elements and if you also consider the group 2 elements like beryllium, magnesium, calcium, barium, strontium, these elements if you consider and their corresponding hydroxide, that is LiOH, NaOH. So formulas for group 1 elements, the formula is MOH, where it is carrying +1 charge because maximum oxidation state for group 1 is +1. But when it is group 2, the formula, general formula is like this, because now M is carrying 2 positive charge. So that is why formulas are different. But whatever it is, the hydroxides of both this group, that is S block, group 1 and group 2, they are actually strong bases because when you take them in water, there is a complete dissociation. Just take KOH, all the molecules of KOH, it will be dissociated to K plus cation and HO minus N, right? Though it is true that group 2 are hydroxides, their solubility in water is not good. That is different issue. But you have to remember, though it is not fully soluble, but the fraction of these hydroxides that are that is the fraction of these hydroxides that are in soluble state, in that portion there is complete dissociation. So here it is mentioned that the group 2 hydroxides are only slightly soluble, not like group 1 hydroxides which are completely soluble, but the portion that does dissolve, that is the dissolved part. Suppose some fraction 50% is in dissolved portion, okay? So the portion that does dissolve, they are now in completely dissociated form, right? So these are examples of strong bases. Then weak bases dissociate only partially in water and they produce hydroxide ions. Many compounds are bases even though they do not contain hydroxide ion, and that we have already seen in the different theories, right? So remember the theories, that is Bronsted theory, Lewis theory, Arrhenius theory. So in Arrhenius theory, we talk about H plus and HO minus when we give the definition of acid base. But when we talk about, especially Lewis, when we talk about, there is no such thing that to call a species base, it has to produce HO minus. No, that is not necessary. So many compounds are bases, even though they are not carrying any hydroxide ion that you can see in these examples. But that is not necessary always. So in those cases, though they are not carrying hydroxide ion, but they can increase the concentration of hydroxide ion in aqueous solution because of their reaction with water. And they are basically Bronsted-Lowry bases. Because if you consider Lewis bases, it is basically electron pair donor. And when you consider the definition of base in Arrhenius, they are basically HO minus producer. But that we are not considering here. We are focusing on Bronsted theory, where it is mentioned that they are basically H plus, they can capture H plus. So if a species can capture H plus, you can call them bases. So here also the same thing we can see. So ammonia, this species Bronsted-Lowry base, because when it is you have taken it in water as solvent, then ammonia can capture the H atom in the form of H plus. And as a result, when H from H2O, one H is taken, the remaining part will be HO minus. So in this way, indirectly it is producing HO minus, right? Because it is capturing the proton from H2. So remaining part is HO minus. So in this way, they can increase the concentration of HO minus ion in aqueous solution because of their reaction with water. So in this example, it is clear that NH3, though there is no HO minus, but as is it capturing H from H2O, so it is ultimately producing hydroxide ion. But remember, this equilibrium that is mentioned here, it is not that all the ammonia can capture H2O molecules, because H2O is present in excess. But ammonia, all the molecules of ammonia cannot undergo this process, that is capturing H from H2. That is only possible in partially possible, and that is weak bases definition. Now strength of bases. So remember, in case of acid, strength of acids, we have used ionization constant K, which is basically equilibrium constant for the ionization of the acid HA in general. Similarly, base ionization constant is denoted by Kb. B means base, and that is the equilibrium constant for the ionization of a base. The conjugate base of a weak acid, this is also a strong base. So this discussion we have done in conjugate acid base pair in the last class. So if we have any weak acid, suppose HA is weak acid, so when it is dissociating, we are getting H plus and we are getting A minus, which is the conjugate base of the acid HA. So this conjugate base of acid HA, that is A minus, that is also strong base. Why it is strong base? Because HA, it is weak, so most of the molecules will try to remain in undissociated form. Only a few fraction of HA will be in A minus form. That means it will not remain in A minus form. So here the equilibrium sign, I can give it like this. So see, both the arrows are not equal. The arrow which is towards right hand side, that arrow is smaller. So it means mostly it will remain in undissociated form HA. So how it is possible? Because A minus is very strong base, because HA is weak. So A minus has to be strong. Strong means what? It will easily capture H plus and it will try to remain in the undissociated form. So A minus, it is not very stable. It is reactive. Reactive means it is strong. Here we have taken this base species, which is denoted by B. So B is denoting, it is indicating the base B, any base B, which is reacting with water, and it is capturing H from H2O. As a result, now BH plus we are getting as cation, and HO minus is produced, which is the remaining part of water. So the value of ionization of a equilibrium constant for the ionization of base, or you can say ionization constant of a base, that is concentration of BH plus cation multiplied by concentration of HO minus anion divided by undissociated B concentration. As usual, we have avoided water because it is present in excess. Okay. Here we have some examples. First column, name of the base, then ionization equation, that is what type of equilibrium is present, what reaction is actually going on, then the Kb values. Fine. So methylamine means CH3NH2, methyl group, then NH2. It is primary amine, 1 degree amine. So it will capture one H, that is proton from H2, and it will be converted to CH3NH3 plus cation. HO minus is generated. Then we have ammonia. This example you have already seen in the previous slide. Then pyridine having formula like this. C5H5N. It is capturing proton itself is converted to C5H5NH. So this N, now there will be hydrogen attached. So N is getting positive charge and HO minus. Then we have acetate ion. So see now the species, that is the base itself, is carrying some negative charge. So that is also a type of base, right? So here the definition that you have to keep in mind, it has to be proton acceptor. Then you can call it base, because in these cases we are considering the Bronsted theory. So CH3COO minus, as it can capture H plus. So now it will be also considered as base and HO minus is produced. Then we have fluoride ion as base, urea as base. Urea, this is the formula NH2CONH2. It actually in like this, NH2, then C double bond O, then another NH2. So when it is protonated, one of the NH2, it will capture proton. Now it is NH3 plus. There is positive charge over this, and HO minus is produced. So Kb values, if you look at the right hand side, as we are moving down from 10 to the minus 4, then minus 5, minus 9. So as we are moving down, basically the value is decreasing, right? So here all among all these examples, the most weak base is urea and the most strong base is methylamine. Though it is true that all of them are basically weak, you cannot call them strong. But relatively, if you want to know the order of their basicity, then among all these examples, from the value of Kb, it is clear, as it is having the lowest power, 10 to the minus 14. So urea among all these examples, that is the weakest base. Okay. Here we have a problem related to whatever we have discussed. So it is saying that which of the following salts, here we have some salts, right? Which of the following salts is most basic when they are in aqueous solution? We have what type of salts? Aluminium, 3 cyano groups attached to it. Then we have potassium salt of acetic acid. Then we have FeCl3 and we have lead acetate, PbCH3COO whole 2. 2 acetate ion together attached to Pb2 plus R. Now these are in salt form. Now we know that what we consider the definition of salt, it is acid plus base and it is producing salt, water. If you consider the reverse reaction, that is hydrolysis of salt. So if you take salt in water, you will get acid and base. Now this acid and base, it may be weak or it may be strong. Now depending on whether the acid is strong or base is strong, the ultimate basicity and acidity of the solution, when you have taken some salt in water, so that will depend on whether this acid and base, that is from which this salt is actually produced, that acid and base, whether it is weak or strong. Depending on that, you can decide that what will be the ultimate nature of this aqueous solution of these salts, whether it will be basic or acidic. So suppose if acid is very weak but the base is very strong, obviously the nature of the aqueous solution will be basic. But if it is reverse, if base is weak but acid is strong, then the ultimate conclusion will be that the solution is acidic in nature. Here what we have to find? We have to find in which case it is most basic, not just basic but most basic. So first we will take AlCN, that is all of these salts one by one we have to take, and we have to see what is the acid and bases from which the salt is produced, right? So aluminium ClO3, it is a salt of weak base AlOH3 and HCl. Okay, and this line is important, that when a salt is made from strong base and weak acid, then only the solution will be basic nature in aqueous solution. So AlCN3, if you mixed AlOH3 with 3 molecules of HCl, then what you will get? You will get Al3Cl In this way, this salt will be produced and there will be total 3 H2O molecules. But if you consider the reverse reaction, it is combination of the weak base ALOH whole 3. Here the acid is also weak. So there is no anything strong. In none of these species is strong. So this is not correct. Then if you consider acetic acid, basically when you take these two together, that is strong base is KOH and acetic acid is not strong, it is weak. So acetate part is combining with K and H is combining with OH part and it is producing water and potassium acetate. But potassium acetate is the salt which is we have made from acetic acid and KOH, and here base is strong. So these can be the correct answer. But we will also see the other two. What about FeCl3? It is made from FeOH whole 3 and HCl. How it is made? If you write this formula, so balanced equation will be like this, because 3Cl you need. So 3HCl I have to write, and 3H, 3OH together it will produce 3H2. But important point is here the initial base is FeOH whole 3, which is obviously not strong, but HCl is strong. So the overall solution, it will be acidic in the third option. And what about the last option? Pb acetate. So starting base is PbOH whole 2 and acetic acid. So in this case, the equation will be PbOH whole 2 and two molecules you have to write to get the balanced equation. And here it is Pb, 2 acetate ion, and how many molecules of water? Here 2H will get from here and 2H, so it will be ultimately 2H. Okay, so this is weak, this is also weak, but one species has to be strong. If you ultimately draw if we are to conclude the fact that whether it is acidic or basic, one of them at least should be strong. So only in second option, here we have strong base KOH. So that is why second option will be the correct option. Fine. So strong acid, strong base, strong, then weak acid, weak base, we have seen in detail. Next topic is ionization of water. So water, we have seen that it can behave as base, it can also behave as acid, and that depends on with what is the other, depending on the other reaction partner. So if you take H2O with ammonia, it can donate proton. If you are taking it with the combination of HCl, now it can accept proton, right? So it depends with which you have mixed water. But if you simply consider water, then also there is some ionization. Forget about any other species. Suppose you have taken only water. So for water itself, there is some ionization. Water has electrical conductivity. That means there must be some cation and anion. And how the presence of cation and anion possible? Only if there is some dissociation. Even if it is very small percentage, but still there is some dissociation of water molecules, and it is producing the cation H plus and the anion HO minus. So then only it can show some electrical conductivity. So it proves, that is electrical conductivity of what it proves, there is some dissociation of H2O molecules. When it is pure water you have taken, there is very little amount of it will be in dissociated form, that is H plus and HO minus. And this type of dissociation, it is called auto-ionization of water, because there is no external agency that is helping. It is going on its own. So that is what is auto-ionization. In water, equilibrium exists between ions and unionized water molecule, that is undissociated water molecule, right? So the equilibrium we'll see, this is neutral water molecule H2O, it will dissociate H plus and HO minus. Now this H plus, it can combine with another neutral water molecule and it can produce hydronium ion. So the net reaction you can write in this way, that is if you add this equation, that is two water molecules, if we add, what we will get? We will get this H plus it will be cancelled. If you add these two equations, H plus it will be cancelled, because here it is present in left and here it is present in the right. So if you add these two equations, the net reaction will be 2 water molecule in the left hand side and 1 H2O plus hydronium ion in the right hand side and 1 HO minus anion in the right hand side. So this is the net reaction. 2 water molecules from 1 water molecule as if we are getting the protonated form, another water molecule as if it is the deprotonated form, which is HO minus. So look at this arrow. This is shorter, this is longer. So it proves that mostly it will remain in left hand side. The equilibrium, it will remain mostly in the left hand side. So this is a hydronium ion, H3O plus. This is the hydroxide ion, HO minus. So there it is written, that is all the bonds are shown. But if we simply consider this equation, it is like this. As if one water molecule is behaving as acid because it is donating proton. So if you are considering this H2O molecule as if it is donating proton, it is now converted to this HO minus. So as if this, here it is written base, but actually it is the conjugate base of H2O. And the second water molecule, it has captured the H plus that is donated by the first water. So obviously that is the reason it is behaving as base, because it is capturing H plus according to bond state theory. So now this H3O plus, this is basically the conjugate acid of this. Fine. So one water molecule it is behaving as acid, it is producing HO minus. Another water molecule is behaving as base, it is producing H3O plus. So that is mentioned in the last statement. Now for this equilibrium, if we write the corresponding equilibrium constant as if it is Kc, so Kc should be equal to concentration of H plus multiplied by concentration of HO minus. So this equation is basically if you write only one water molecule undergoing dissociation, then this type of equilibrium you will get. So H plus and HO minus. For this equilibrium, the corresponding equilibrium constant, it will be concentration of H plus, concentration of HO minus, then divided by H2. You can also write it like this. I am not saying this is anything wrong. So now you have to write H3O plus and HO minus. So in this case, the Kc value, it will be concentration of H3O plus, concentration of HO minus divided by concentration of H2O to the power 2. But remember, whether you consider this one or this one, it doesn't matter anything. In both cases, the denominator, that is a concentration of H2O, and for the second case, concentration of H2O to the power 2, whatever it is, as concentration of H2O is very high, so as if it is constant, and practically H3O plus is equal to H plus. So that is the reason ultimately we can write Kc is equal to concentration of H plus and HO minus only. So from this part, first we have not written Kw, this is the ultimate expression. First we have written Kc because ultimately this concentration, this is constant. So this constant part, if you are multiplying with Kc, you are getting another constant, which is now Kw. So the final expression for ionization constant of water, considering these two conditions, now it will be that is H plus concentration multiplied by hydroxide ion concentration. Okay. Now we will see in detail what is ionization constant of water, that is Kw. W signifies water. Okay, that is why we are using the subscript W. It represents the ionic product or ionization constant. Both terms you can use of water. So when it is pure water, you have taken in 25 degrees centigrade, it is found that a concentration of hydronium ion or H plus ion, whatever it is 10 to the power minus 7 moles per liter. And as these two are always same, because from one water molecule, if you consider, you will get one H plus. So the number of H plus and the number of HO minus, it is always same. So if concentration for hydronium ion or H plus, if it is 10 to the minus 7, so obviously for hydroxide also it is 10 to the minus 7. Okay. Now this is the expression. So in place of hydronium ion, you can write this. In place of HO minus concentration, you can write this. So ultimately, the value of Kw at 20, don't forget to mention at 25 degrees centigrade, because we know equilibrium constant, its value changes with temperature. So temperature you should mention. Okay. So this is the value for Kw, that is ionic product value for water, but it is at 25 degrees centigrade, 10 to the minus 14. Now, like all equilibrium constant, this is also constant, because this is also a kind of equilibrium constant. So this should be also, it should be mentioned at a particular temperature because of its dependency on temperature. So it is constant only at a particular temperature. So when you are changing the temperature, its value will also change. The dissociation of water, it is endothermic process. That means when you increase the temperature, we know how Kw value, it is dependent on temperature. From Van der Waals equation we have already discussed that. So Kw value, as it is endothermic, with increase in the value, increase in temperature, the concentration of these hydronium ion and HO minus ion, it will increase, because now more and more water molecule will be in dissociated form. It is endothermic. The process will be shifting from left to right more and more. So H2O plus concentration, HO minus concentration, this will increase. And as a result, the ionic product, that will also increase, because if this side is increasing, Kw is also increasing. So now we will see from this table, you can understand. Here we have different temperatures starting from 0 up to 50. This value we have already calculated here. But what about lower temperature, 0 or 10? What about higher temperature compared to 25? See, 40 and 50, the value is increased. Here it is 10 to the minus 14 into 1. Here it is 2.71 into 10 to the 14. Though power is not changing. So you can say one fact is clear, though there is increase in Kw value, but the increase is not so significant, because power of 10 is still minus 14. Only this part, from 1 now it is 2.71, at 50 it is 5.30. Similarly, when you decrease temperature, now look at this value, it is 10 to the minus 50. So its value is less compared to 25. So when we are increasing temperature, Kw is also increasing, though it is not so different from the initial value of 25, but obviously there is increase, right? Some more information regarding ionization constant of water. When a small amount of acid, so until now we have seen we are dealing with pure water. We have not mixed any HCl, that is any acid or base, that we have not mixed. But suppose you are mixing some small amount of acid, just take this simple acid HCl. You are adding HCl to water. Now obviously the concentration of H plus and concentration of HO minus, you cannot write these two are same. Now it is not equal, because you have added extra H plus. So this is the case now. And H plus concentration is no longer 10 to the minus 7, as you have seen at 25 degrees centigrade. It is 10 to the minus 7, but when you have added some acid, now it is greater than 10 to the minus moles per liter, or dm minus 3. Similarly, if you add any base, for example, you have added NaOH. Now concentration of HO minus H plus no longer equal, concentration of HO minus is high, and it is greater than 10 to the minus 7 moles per dl. But if it is neutral solution means it can be pure water, or it may be any solution where there is any salt like NaCl. What type of salt? It should be a salt, only those type of salts which is made from strong acid and strong base. So NaCl salt, if you consider, it is made from HCl and NaOH. If you add NaOH HCl, it will produce NaCl, and H and OH, it will produce water. So NaCl is such a salt which is made from strong acid, strong base. So in these cases, if you take NaCl in water, after all, ultimately after salt hydrolysis, it will produce HCl, NaOH. But here, as both HCl and NaOH, they are present in equal amount. That is same number of moles. From 1 mole of NaCl, you will get 1 mole of HCl and 1 mole of NaOH. Now, if these two are present in same concentration, that means here concentration of H plus and concentration of HO minus both are same. Both are strong. These are dissociation complete. And if there is X moles of HCl, there is also X moles of NaOH. So same number of H plus, same number of HO minus. So again, you can say that this is neutral. So again, they are equal to 10 to minus 7. So not only neutral water, because in neutral water both are equal to 10 to minus 7, but even if it is some salt like NaCl, you are taking it in water, then also H plus HO minus, their concentration same, and you can write it is equal to 10 to the minus 7 moles per dm cube. The concept of ionic products of water, it helps us in classifying aqueous solution whether it is acidic, basic or neutral. So when it is neutral, the value of Kw, as we have seen, H plus HO minus, it is 10 to the power minus 7. But what about the ionic product? If it is not neutral, suppose if it is acidic or basic, then what type of change we can expect? That we'll see now. So to understand it, there is a new topic which is basically pH scale. So when we deal with some acidic solution or basic solution, that is, it is no longer neutral solution, then mostly the concentration range is 10 to the power minus 1 to up to 10 to the power minus 7. Mostly it is dilute solution and it ranges in between these two values. So if we want to express the strength of this as solution, whether it is acidic or basic, with such low concentration, it is very low concentration, then scientist Sorensen introduced a convenient scale which is basically logarithmic scale, and this scale is known as pH scale. And what is its purpose? Its purpose is to express hydrogen ion concentration, because once you know the hydrogen ion concentration, you can decide acidic, whether the solution is acidic, whether it is alkaline or neutral. So in the previous slide, what we have seen, that the concept of ionic products of water, it helps us in classifying aqueous solution, whether it is acidic, basic or neutral. Now don't think that it is saying that Kw value will change when you have added some acid or base. When it is neutral, we know it is 10 to the power minus 14 at 25 degrees centigrade. But don't think when you are adding some acid or base, it will change. Basically, it is true when you are adding some acid, it will be now the condition. When you are adding some base, this will be the condition. So individual HO minus, it will increase. Individual H plus will increase in these two cases. But the overall Kw, that is always 10 to the power minus 14. Because that is dependent only on temperature. Whether you add acid or base, it doesn't matter. It is true when you are adding acid. Remember Le-Chatelier principle? When you are adding excess H plus, then concentration, that is equilibrium, now it will manage itself in such a way so that it can counteract on this effect. So you have added extra H plus. It will adjust the equilibrium in such a way so that the Kw value, it is still the same. Okay? But H plus concentration will change when you add HCl or you are adding some base. So that is why it is important for us to know what is the H plus ion concentration when you are adding some acid. Externally you are adding some HCl, that is in general any acid or base, to neutral water. Then what is the effect on H plus? And that information you can get from this pH scale. So that is the purpose of pH scale. We want to know what is H plus ion concentration, but H plus ion concentration directly we do not express in this form, that is 10 to the minus 7, because handling these numbers are little different. There is power of 10 and it is negative. But pH scale, when you will actually see it, you will see that dealing with these values in day-to-day life, it is easier. So that is the importance of pH scale. This is logarithmic scale. And if you know the pH of the solution, you will be able to predict whether it is acidic, alkaline, or neutral. So how we can define it? pH of a solution is defined as the negative logarithm of base 10. Base 10 means we will use log, not ln, and there will be negative sign. Negative logarithm of base 10 of the molar concentration of H3O plus, or you can write H plus, both are same, that is present in the solution. So this is the expression we use to denote pH. Negative, then log 10, even if you do not write 10, it is okay. Simply we write minus log H plus concentration. So pH means, if you know H plus, just put the value here and then take log, and H plus as it is in the range 10 to the power minus 1 to 10 to the power minus 7. So when you take log, that will be a negative value. And there is already negative sign, so 2 negative, it will be cancelled and it will be positive. So in reverse order, if you write H2O plus concentration or H plus concentration, that is equal to 10 to the power minus pH. Minus is before pH, like this, 10 to the power minus pH. So H2O plus, you can also write it as if it is anti-log of minus pH, or you can write 10 to the power minus pH. Okay, but expression of pH is like this. The pH scale expresses all degrees of acidity or alkalinity, but it is only for dilute solution where the ranges are like this, not for concentrated. So pH of a solution, here we have one example. So it is, sorry, here it is subscript, not like this, minus log 10 H2O plus, and suppose H2O plus is 10 to the power minus 7. So we have written in place of H2O plus concentration, we have written 10 to the power minus 7. So when you take log, this power of 10, it will come before log and it will be minus 7. There is already one negative sign, so two negative sign together will be positive, and log 10 is simply 1. So 7 into 1, ultimately the pH is 7. So in this way you can calculate that is the pH of the solution. Similarly, now you know what is the pH. So if I now ask you what will be the H2O plus concentration or H plus concentration. So H plus concentration will be 10 to the power minus pH. And what is pH? pH is 7. So it will be 10 to the power minus 7. So this is the concentration that you have already put here. Okay. So reverse order, you will find, suppose if pH is mentioned and it is asked that calculate the concentration, then you have to proceed in this way. And if H2O plus concentration is given, then put it in, that is log of it you have to take, then you have to consider negative sign so that the negative sign is cancelled. Ultimately pH value, it will be something positive value, and its value, the range is starting from 1 up to 14. Which of the following salts will give highest pH in water? Now highest pH means you have to, it is not that you have to calculate it because concentrations are not given. Now highest pH means there is a range from 1 to 14, right? So if it is towards lower side, it means it is acidic. If it is around 7, it is neutral, and if it is moving beyond 7, 8, 9, 10, 12, then it is basic. Okay. Now highest pH basically means it is basic solution. But how to know which one is basic and how the pH range works, that we will discuss in detail in the next class. So this problem also we will discuss in the next class. We are at the end of the session. Thank you for listening.